Okay, so we're going to continue today talking about multi-component phase diagrams, and in particular we're going to be talking about naturally occurring what's referred to as petroleum reservoir fluids. And what's meant by petroleum, if you look it up in the dictionary, it's calling it a liquid hydrocarbon mixture, which is not really how we're using the term here. We're basically talking about naturally occurring hydrocarbon reservoir fluids, but for convention I'm just going to say like it's petroleum engineering. If you look up on Wikipedia or any of the dictionaries, petroleum is going to be generally defined as a liquid hydrocarbon mixture, which is not what we're really talking about here. We could be talking about gases or liquids or I don't know kinds of fluids. So these naturally occurring reservoir fluids will typically consist of certainly in the very simplest case 10-20 components. That would be a very simple gas, very boring kind of gas, but much more often in the great majority of reservoir fluids will contain hundreds if not thousands of different compounds, hydrocarbon compounds for the most part, together with nitrogen, CO2, H2S, primarily as the non-hydrocarbons. So we're talking about so many compounds that it's difficult to get your hands or your mind around them. What I've tried to convey in the first lectures is that which compounds we have. So for example, compounds with 6 carbon numbers, you have many isomers to pick from. If you have more aromatic, more benzene than you have normal, or vice versa, then it will affect what we call the phase behavior of that mixture at some pressure and temperature. It might define it having being a gas or an oil in terms of some definition that we want to pick. It might determine whether at initial conditions it's got a certain saturation pressure, bubble point or dew point at a given temperature, and so forth. So it's which compounds are in the mixture and the amount of each compound. And the quantification of the amount is done in one of 2 ways, and those 2 ways are what? Mole fraction on a molar basis, or
weight fraction.
Yeah, they call it weight fractions in America, but it's actually mass fractions. Okay, mass fractions, weight fractions, or mole fractions. And the laboratory is for the most part measuring quantities in terms of mass. The experimental equipment they use generally quantifies in terms of mass, and then we convert it to moles using molecular weights of each component, which we know for CO2 and methane with 4 or 5 digits of significant digits, but we don't know it for all of the components heavier than C6, C7, okay, or a given C7 compound, single carbon number with C7 for a given mixture. It might be purely alkanes, or it might be primarily benzene and a little bit of alkanes, and its properties would vary. The molecular weight, I think, of benzene is what? I know the molecular weight of benzene. Now, benzene is part of the C7 component by convention. Okay, so it's. I know the molecular weight of benzene. There's how many carbons are there? 6. And what's the molecular weight of carbon? 12. And then there's 6 hydrogens, so you get what? Huh? 78, I think. Yeah. Okay. So the molecular weight of normal heptane, which is at the other end of the scale for C7, the molecular weight is 14 times 7 plus 2, which is 100. So it can go from 78 to 100, the molecular weight of what we might call C7. The laboratory might call it C7. Now, it would be extreme to have only benzene. That would be an extreme fluid. Okay? But that is the range, the potential range of molecular weight for the so-called C7 component. Table 5.2 in the book gives a set of average. We just kind of like, average, somebody's average. The guy's name is Donald Katz. This is the professor of Standing who was here, etc., etc. This is from his collection of samples back around 1978 when a fellow named Abbas Firzabadi stopped by at the University of Michigan for a year or so. They put together a collection of average properties for single carbon numbers that was in Donald Katz's library of reservoirs from around the world, I suppose. And there you have C7 has an average molecular weight for an average reservoir fluid of, I don't know what it is, but we'll go find it. And first I have to find the monograph. Let's see here. Let's see, table 5.2, I don't think it'll find it, but getting close. So, you see, Katz and Firzabadi, lying to you, his name is Abbas, that's his first name. Donald Katz, let's see, carbon fraction number, this is actually should be single carbon number, normal boiling point, I think from normal C6 to normal C7, and then we've got an average molecular weight in his library of 96, which kind of makes sense. Primarily made up of alkanes, which has a molecular weight of 102. But your reservoir fluid might have an average molecular weight of the C7 of 101. It might have an average of 90. Okay? And accordingly, with the different particular compound and the amount of them, we're going to get different what we call phase behavior. And so far, phase behavior has been related to defining if it's gas or oil, or whether it has a bubble point or a dew point at a given pressure. Okay. Phase diagrams that we've been talking about so far, mainly this is the pressure temperature diagram. We're also going to look at a pressure volume. We've already looked at pressure total volume for single components and two components. We're going to do a special version of this where we plot pressure versus the relative percentage of the volume that's oil. Okay? So if it's 100% oil, then it's at a bubble point. If it's 0% oil, it's at a dew point. Okay? If it's 50%, it's got 50 volumetric percent. So that we're going to call a relative oil volume, and that's one of the new phase diagrams that we'll look at. It's kind of looking inside where we have two phases and the edges of where we have single phase. Then we're going to look at something called a pressure composition. I'm not going to write it with I, but a pressure composition diagram that also is considered a phase diagram. And then finally, I'm not sure if it would be called, it is kind of a phase diagram, what's called a ternary diagram. I'll call it light, intermediate, heavy diagram. And all of these, the purpose of the phase diagram is primarily orientation I'm just going to move, give myself a little more room here. Its orientation. About what? Okay. Young lady in the back with next to the last row. I don't know names yet. Yes, with you have something in your hair. Yeah. So what is it in the orientation about the phase diagram? What is it kind of telling us? It's mapping out something.
The phases.
Phases, and what about the phases? Liquid or vapor or
Mixture.
well, it's always a mixture, unless it's a single component. Both vapor and liquid. That's not the same as mixture. Mixtures, okay? Right. So it's trying to map out or orient us about, is it a single phase or is it two phases? Might be telling you where it's three phases as well. But that's what it's the purpose of the phase diagram. And we have all sorts of them. We've got pressure, temperature, pressure, volume, pressure composition, and the so-called ternary diagram. And that's what we're going to talk about today. But we're going to talk about it for real petroleum reservoir fluids. Okay? And then towards the end of the day, I hope, we're going to talk about how does nature make the decision that a given composition, Zi, at a given pressure and temperature is single phase or two phase. Okay, what's the question that Mother Nature is asking? Because, it just happens. Mother Nature just pops it into one phase, two phase, and you have to shake it up a little bit, help out Mother Nature. If you don't shake it up, it takes time. It might take days, might take seconds, might take millions of years. But if you can shake it up, then you help Mother Nature get to where she knows where she wants to go. Okay? Single phase or two phase. And then we're going to talk next week about calculating, doing for Mother Nature, calculating, because you can't call Mother Nature as an engineer and say, oh, what pipeline is going to have two phases? Are we going to have water condensing out of the gas? Or we're going to have problems? We're going to have to dimension the pipe larger, smaller? Or we're going to have to pig the pipe? We can't call Mother Nature and ask the questions. So we have to do calculations, right? And those calculations is what you guys are supposed to be doing as a job to get paid. And that we're going to be kind of working our way into next week, the calculations. Now we're just kind of figuring out what the calculations will let us give orientation to the boss who doesn't understand the calculation. The boss just wants to know, is it single phase or two phase? Do I need a bigger pipeline or a smaller pipeline or bigger tubing or smaller tubing, etc., etc. And all of those calculations of flow through, reservoir flow through pipe, it's strongly influenced by whether it's single phase or two phase. Okay? Generally speaking, two phase requires higher pressure drop, and higher pressure drop requires, in general, more cost, more money. Okay? And we're in the mode of saving money in the industry, so, okay. So that's why we're doing this stuff. Single phase or two phase. All right. And we're moving out of single components and out of two components. We're moving into actual mixtures. So I'm going to sketch for you first the pressure temperature diagram, a generic temperature diagram for a petroleum reservoir mixture. Okay, so pressure temperature. I'm going to make a sketch. If I'm lucky, it'll and then this thing here down below is going to be so hugging the axis that you something like that. It could be smaller, it could be bigger, but generally speaking, this is what it's going to look like. And inside here, inside the envelope, we have basically two phases. Everywhere inside here. And the start of two phases is the line itself. Okay? If you're on the line and you're about to fall into the inside, if you're falling in there, you'll see either the bubble appear or the droplet appear. Okay? So you're at the point of a second phase appearing. So we also consider the line itself part of the two-phase region, even though the second phase is epsilon. All right? Outside that, it's single phase. Everywhere outside it, it's single phase. Out here. Okay? Now, somewhere along here, and I'm just going to mark a point. This point it's not at the very top of the maximum pressure. It's not at the top. It could be down here. It could be way over here. But that point differentiates the line of bubble points. So this is the line of bubble points, the bubble point line. Okay? Okay, and by the way, this whole pressure temperature diagram is for a constant or fixed composition, Zi. It's very important that you remember this, that if I ask you to draw a pressure temperature diagram, that it applies to one specific composition. Okay? And along that line, that composition, along the pressure temperature of that line, that composition is just forming a bubble. Okay? It's just forming a little bubble, an epsilon small, tiny little bubble. And on the other side of this double circle thing, that same composition here, along this line here, and I'm going to kind of take it to this point, and then I'm going to flip it over to pink. Okay. Along this red line, we have a dew point. That mixture is just condensing out a little droplet of liquid. Okay? Like this morning when you're out scraping the car, at least if you have a car, okay, and you walk back in to the house where it's warm and you get condensed little droplets on your glasses, that's condensation. So you're getting condensation out of a gas. Okay, like you're getting water dropping out of the air in your house onto your glasses. So you're getting condensation along that red curve, but this red curve is called the upper dew point because the pink is also a line of pressure and temperature where if you don't fall down, but if you fall up in pressure into the two-phase region, then you'll also see the droplet of liquid appearing. Okay? So it'll condense by increasing the pressure from here to here, going upwards. Here you're going downwards and you get condensation. And we're going to call the red curve an upper dew point line. And that's the one we're generally concerned about in petroleum reservoir engineering, in petroleum reservoir and maybe not production engineering. And then this lower one down here, we just call the lower dew point. And at any temperature in our system, reservoir to surface, okay, from reservoir to surface, that lower dew point will typically be less than 1 atmosphere, okay, which means way down here, okay. You cannot almost go to the laboratory and take a reservoir mixture and go to a very low pressure and get everything to become single-phase gas with one little droplet of liquid. So typically speaking, in the range of conditions in the reservoir, and I probably should have drawn this even further down here, the lower dew point usually is so low it's of no interest. Okay? It's not at a pressure of any interest for petroleum reservoir fluids. Now, for a separator gas, it's different. But we've got this lower dew point, and we got the upper dew point, we got the bubble point line. That's always going to be in one of these pressure temperature diagrams. The critical point here, we'll just call it critical point, and we've got bubble point. So the critical point could be here, it could be down here. Can you guys see it could be down here, it could be up here, it could be way over here on the right. Okay? So where that critical point, the tie between bubble point and dew point occurs, can be kind of anywhere. And it depends on which compounds are in the mixture and how much of each compound. Okay? So that location, and in fact the size of the envelope, the maximum temperature out here, remember we called this something, it's not particularly interesting, we called it the cricondotherm. Okay? And outside, at any temperature higher than that, it's single phase, no matter what the pressure, right? This temperature here is what we call the critical temperature of the mixture, Zi. Along this bubble point line, we have 100% liquid, right? Well, 100 minus epsilon, which is 100. Okay? For the dew point, we have epsilon, or I'm going to call it 0% liquid. And inside, it's got two phases. Now I'm going to draw a line of where you have 50% gas and 50% liquid, 50% vapor, 50% liquid. I'm going to draw that line. Okay? And like all other 10%, 90%, 63.2%, they all start from the critical point. So the 50% line is going to look probably something like this. I'm going to %50 liquid, and that doesn't look like a 5, so let's 50% liquid. So along that pressure and temperature line, we've got specifically 50% by volume or by moles or whatever you want. Let's say volume, and this line would be 90%, for example. Again, starting from the critical point, 90% liquid. 10% liquid would probably look something like this. Okay? And you get the idea. Okay. Okay, so the critical point, the bubble point versus temperature, which is basically the green curve, the dew point versus temperature, okay, this makes up our phase diagram. These are all primarily a function of Z, well, they're basically a function of Zi. Zi, when you say Zi, it's both the quantity, the molar quantities of each component, but it's also the list of which components, right? So it's got both of these things. So it's a function of composition. Any questions about this? Okay.
Is there any significance of the maximum pressure?
Well, it's just that at any higher temp, the maximum pressure. Well, at any, okay, and this maximum pressure, which is not at the critical point, it's a little bit above there. Let's just mark this as the maximum pressure. Okay? The maximum pressure is called the let's see. Cricondon must mean maximum in some weird language. Does anybody know what cricondon comes from? I don't know. Huh?
Maybe Latin.
Maybe Latin, yeah. Okay. Cricondon obviously means maximum. The maximum bar pressure. Okay?
So the temperature you had is actually the Cricondon term?
The Cricondon therm is the maximum temperature.
So it's not related to the second critical point? I thought it's,
No, there is... No. What we mean by maximum is that any temperature above that, it's always single phase, independent of the pressure, right? If you go to the Cricondon bar, P maximum, any pressure above that, single phase, at any temperature. Okay?
It can be vapor or liquid.
Well, we can stick a label on it depending on how you want to define the label of gas and oil. We come back to that. Okay? But it's all single phase out here. Everywhere out here it's single phase. I'm going to need this real estate here, so I'll take it away. But everywhere out there it's single phase. Okay? Okay. Now I'm going to draw one more here, just for the fun of it. Maybe 30% or something, maybe 20%. Okay. Now, we're going to mark on this figure. Well, okay. Let's come back, in fact, to the question. What's a gas and what's an oil? Okay? What's a gas and what's an oil? Well, convention. This is not coming from above. Nature doesn't, okay? We can choose any definition we like of gas and vapor and liquid, okay? It's our choice. If it's single phase, you can choose. You just have to be consistent. The one way to do it, which is the conventional way to do it in the petroleum industry, is to say that if this is the mixture in my reservoir, okay? If this is the overall composition in my reservoir, and the reservoir has one temperature, okay? Some average temperature, okay? So if that average reservoir temperature is less than the critical temperature of that mixture, okay, then we're going to call this a reservoir oil, okay? That's convention. If the reservoir temperature for this mixture is greater than the critical temperature out here, then we're going to call it a reservoir gas. Okay? But it's just convention. And it really only matters, so to speak, as far as I know, it only really matters when it comes to ownership of sellable oil from the reservoir, goes to the government, if it's a reservoir oil or if it's a reservoir gas. So in Saudi Arabia, it's one definition. In the Arab Emirates and maybe some of the other countries in the Middle East, it's if it's reservoir gas and you get oil at the surface, the government owns it. Okay? So it's very few situations where it really makes a difference. But when it does make a difference, it's a big deal. And this would probably be the convention. I don't know if it's in the contracts or not, but that's probably the convention that they would argue in court. I own this sellable oil or not. Okay? Another definition, which is more consistent in my opinion, for example, but nobody would be using it, is that we look at the density at the critical point, okay? The density at the critical point, and we simply say at what pressures and temperatures in the single phase region do I have that same density? Okay? I'm going to draw that in purple, maybe make it a little bit thicker, and of course it's of no interest because no country is going to. But that line might look something like that. Okay? Where that line is defining the density of the mixture is equal to the density at the critical point. And then I could say if you're on the right side of that, it's a gas, and if you're on the left side of that, you're an oil. So basically you just say, is the density of my single phase mixture greater than or less than that critical density? I could use that for my own sake, but it would just be my, the Curtis definition of a reservoir gas and a reservoir oil. Probably wouldn't carry any weight. But it's equally good definition to using the critical temperature, in my opinion. But of course, convention is sometimes what works. I mean, that's what is used, convention. So typically, we're going to say that if the reservoir temperature is less than this critical, it's an oil, reservoir oil, and if the reservoir temperature is greater than the critical, it's a reservoir gas. Now, if the reservoir pressure is inside the two-phase envelope, then what do we have? Not a mixture, but both. You have reservoir gas and reservoir oil, both. So the reservoir contains both reservoir gas and reservoir oil, if the reservoir pressure is inside the two-phase envelope. So if you take the Troll field in Norway, I've told you about this example. It's essentially the biggest gas and oil field in Norway. The total composition, which probably nobody knows, but if you took the total composition at 2,100 pounds, the initial pressure and reservoir temperature, I don't remember, it would be two phases. So you have a reservoir gas, big old reservoir gas cap, a thin little reservoir oil of 5 billion barrels, okay? And that's a reservoir gas, reservoir oil system, two-phase, okay? Okay, so now I'm going to, I think, do the following. I'm going to say, if we look at, well, the way I've drawn this is kind of, can I resketch the right side of this just to make it a little bit more? I know this is cheating, but okay. Give me a little break here. I'm going to make this maximum right there, and then let it go down like that. So we had this as being kind of reddish and pinkish, like that. Okay. Anybody upset? All right. Thanks. It'll make it look nicer. So what I'm going to do now is I'm going to take one of these curves, like the 10% liquid dropout curve, okay? And what we see is that there's a maximum temperature, and I'm going to mark that like this. If you go to the 20% line, that maximum temperature may be right here. And up here, the maximum temperature, it's kind of hard to say where it's at, but I'm just going to mark those points. And then I'm going to join them with a line, which is going to go pretty much straight down. Okay. Now, why did I do that? So the reason I did that is because condensation is a term. Let's make a note down here. Condensation. What does that mean? It means the appearance of a liquid phase from a gas phase, from a gas. Okay? And so if we just take some temperature, it can be any temperature in this region over here. If our reservoir, let's say our reservoir initial pressure was up here, okay, and we're dropping the pressure by producing out, and then we hit the dew point, right? So what's going to happen as we take stuff out of the reservoir, gas, mixture out of the reservoir, the pressure in the reservoir sinking, okay, because we're taking stuff out. So the reservoir pressure is dropping as we produce. We reach this pressure, and then as we go just inside the two-phase envelope throughout the reservoir, where the pressure is less than that dew point, you'll start seeing a liquid phase appear, some measurable saturation of liquid oil. It's called condensation. Okay? And coming from initial reservoir pressure going downwards, that amount of liquid that we get as we continue to lower the pressure, right, is increasing. Just past 10%, right? We just keep going down. But at this point, when it reaches this dashed line, its value is now 14, 13%. Okay? So it's been increasing from 0 to 13%. As you go to a lower pressure now, it drops to 12, to 11, and then back down to 10. So now something else is going on. We're getting less condensate, or something else is going on. So in this region where we're getting increasing condensation, as you lower the pressure, that's referred to as retrograde condensation. Problem is I want to use this area on the right at some point. So we're going to call retrograde condensation where you get increasing liquid, I'm just going to say volume or amount, as pressure decreases. Okay? It's called retrograde condensation. As pressure decreases. So the liquid volume is increasing from 0 to 10% to 13%. In that region there, we've got retrograde condensation. And I'll just call it RC. Okay? Retrograde condensation. And within that envelope, from the upper dew point, red line, down to the dashed line I've drawn, that's where you see retrograde condensation. That's where you satisfy that Decreasing pressure gives increasing amount of liquid. Below there, as you decrease the pressure, the amount of condensation decreases. Okay? So, what does retrograde mean? I don't know, maybe it's a Latin word again. Okay? Retrograde, I think, you have to look it up. Before Google, I supposedly learned what this means. I think it means the opposite of normal. Okay? Kind of the opposite of normal. What does that mean? Well, that means that the normal condensation that people understood was that as you raise the pressure, you get condensation, increasing amounts. And that's what would be down here. If you start down here, which you obviously won't, but if you had this mixture and you started at a very low pressure and you started increasing the pressure, you would get increasing condensation as the pressure increased, right? I should have. That's called normal condensation. And that's because for simple mixtures in the late 1800s, scientists observing gas, vapor, liquid phase behavior, they worked, in the 1800s, they didn't have high pressure containers and stuff. So they were looking at systems at low pressures. And what they found is that some systems, as you raise the pressure, you got condensation. That was the normal. Okay? So all the observations of condensation, a liquid appearing from a gas, was from a low pressure up towards a high pressure. So that's what the Dutch and other people who were doing this stuff in the 1800s made that observation. They called it just condensation. But in the 1930s, people like Donald Katz in the 40s, around 1940, in fact, there's a paper written on retrograde where they turn retrograde condensation. A guy named Katz was the first author, and Curat, I think, was one of his students or a colleague, and they wrote this paper on the observation of retrograde condensation in petroleum reservoir systems. That was the norm, that you would start at a high pressure, lower the pressure, and see condensation increasing. That was unusual. That was the opposite of the normal. So they coined it retrograde condensation. And inside this area, between the dashed line and the red line, that's the area of retrograde condensation. Okay? And that's a term you're going to hear the rest of your lives if you stay in this business. Now, because reservoirs will continue down in pressure, you'll, generally speaking, go monotonically down in pressure normally. What happens when you actually start seeing the liquid volume to decrease in the petroleum reservoir? They don't call it, oh, now it's normal condensation. They don't call it that because now the condensate volume is decreasing. So they call that the region of vaporization. We're revaporizing liquid that condensed out first from here to here. Now we're revaporizing some of that liquid back into the gas. Fordamping in Norwegian. So we're revaporizing liquid as you go down in pressure. Okay? So you have retrograde condensation first, then revaporization of some of that liquid back into the gas below the dashed line here. So that's revaporization. It's not talked about too much, but so that would be below the dashed line, retrograde condensation. Where the liquid volume decreases as pressure decreases. Okay? Okay, any questions before we take a break? This is the standard pressure temperature diagram.
For the dashed line, does it stop in the 50% liquid always, like when you find the highest temperature at each percentage? Or is that just because you draw it this way?
The way I've drawn it, I mean, the 50% liquid line could be on the left side of the dash. In other words, it could be like I've drawn it, or it could be that the 50% line is...
No, like, what's the definition of how you identify these points? You said the maximum temperature of each line, right?
Yeah, basically if you take a certain percentage, 50%, you take the maximum, if it has a maximum, okay? So you have to do it for every percentage that has a maximum. You just join those points until you reach the Criconden therm.
Okay.
Yeah, and then that defines the region of retrograde condensation. Okay. Okay, we'll take a